I now move to our final talk of the session, which is a duo of Darren Koppel from the Australian Institute for Marine Science and Tom Cresswell from Australia's Nuclear Science and Technology Organisation, and their talk on naturally occurring radioactive material and Mercury risk framework. And this is in collaboration with the National Decommissioning Research Initiative. Good to see you online, and I'll pass over to you. Thank you.
Thank you very much. We're both very excited to be here. My name's Darren. I'm joined by Tom online, and thrilled to be discussing our risk assessment framework funded by the National Decommissioning Research Initiative. And like Dr. Saragold's work, it's looking at the future risk of potential releases of contaminants, specifically naturally occurring radioactive materials, so NORM or mercury, from infrastructure were it to be decommissioned in situ. So our inventory estimates are maybe a little bit different to the North Sea, but they are concentrated into 3 different oil and gas basins around Australia. And they're anticipating about 6,000 kilometers of pipelines, as well as a number of topsides, FPSOs, and other structures. It's quite a costly effort to remove everything, and the current contaminant inventories for NORM and mercury in the tens to hundreds of tons, so a credible risk in terms of those contaminants. In Australia, we maybe operate on a different regulatory framework to the North Sea. The base case, the default regulatory position is complete removal. So any infrastructure that was put in the ocean is expected to come out at the end of its life, and that includes pipelines as well as footings and concrete gravity structures. So there's no inherent exclusions, but there is a path to leave infrastructure in situ where these conditions can be satisfied. So they're quite outcomes-based. They're looking at acceptable levels of impacts and risks, as well as adhering to our principles of ecologically sustainable development and meeting our international treaty obligations. And that includes our obligations under the Minamata Convention on Mercury, the London Sea Dumping Convention and Protocol, as well as UNCLOS as the key ones. And just to highlight, the Sea Dumping Convention does have bans on the dumping of mercury and NORM-contaminated wastes above de minimis levels. So our offshore regulator, NOPSEMA, decides whether impacts or risks are acceptable based on published guidance, industry standards, and best practice guides. And so some of the challenges offshore oil and gas operators have had putting cases forward for in situ decommissioning have led them to develop an environmental risk assessment framework for some of these priority contaminants. So that's where Tom and I came in and developed the framework that you can see on the screen here. It is available now on the NDRI research website, and I encourage you to go have a look. Our hope with this framework is that it would clarify the data needs for assessments and start to align some of those regulatory requirements to the available science for risk assessments to ensure that those assessments are appropriate to contaminants. And Christoph gave a wonderful background to environmental chemistry of contaminants, highlighting some of their differences. What this framework isn't is formal guidance from the regulators, though we did develop it in collaboration with them. So Tom and I, representing Ames and Ansto, led the work. We were supported by an independent advisory group that included 3 of our key Australian government regulators, as well as some independent experts from the university sector. And it was funded and review was provided by the National Decommissioning Research Initiative, including Sarah Goll, who was on our independent scientific advisory board. So this figure summarizes the assessment framework. I don't expect you to read all of it. If you've ever looked at contaminant risk assessments before, I'm hoping that these 3 steps are familiar: the problem formulation, exposure and effects characterization, and risk characterization steps. Nestled within them are what we've defined as critical elements. So these are aspects specific to decommissioning that we think must be considered to inform a risk conclusion for contaminants in this context. And hopefully some of them are pretty no-brainer to you, including quantify the contaminant inventory. Now, these critical elements really reflect existing requirements in our different sets of regulation for decommissioning. So in theory, they're nothing new. They're just packaged in a way that better reflects the exposure scenario that we're dealing with, that in situ decommissioning exposure scenario. We've also included a bit of what we consider best practice, such as the use of conceptual models and uncertainty assessments, just to round out the framework. We've also included an annex of one-page indicators in the framework, which provides practical guidance, really the nitty-gritty of Norman Mercury assessments and types of evidence that can be collected and presented to inform this assessment. So there's the high-level work as well as a bit more practical guidance for proponents. Our hope with this framework is that it's applied quite flexibly, so it only needs to be as complicated as the nature and scale of the decommissioning activity warrants. We're encouraging that it's applied iteratively, so our recommendation is to start desktop consolidating all the information that proponents can collect before going out to the field or looking at laboratory investigations. And although we've developed the framework for Norman Mercury, we believe at the highest level it should be applicable to other contaminants. We do recognize that this is one small part of the decision making that goes into the most optimal end-of-life management of infrastructure, and we're hoping that this type of framework and the information gathered following this framework can feed into comparative assessments and net environmental benefit assessments. But it's not intended to be those. It's intended to only focus on the contaminants. So I'll step through a couple key concepts that we've brought into this framework. The first is on the use of conceptual models. In other applications, they can be pictorial or process-based, which is what I'm showing here, where we talk through some of those environmental processes that affect contaminant sources, their effects to receptors, and the impacts of the values that our environmental legislation is seeking to protect. One of the reasons why we really encourage the use of conceptual models in this context is because it facilitates risk communication, which we thought was quite lacking in previous assessments. It also puts a lot of the hypotheses and assumptions around risk assessments and risk conclusions on the table and provides testable hypotheses about the impact pathways from contaminant source to those receptors. So we think it does a good job of communicating all of that and organizing information. The other concept we've introduced is around the use of weight of evidence and multiple lines of evidence. There's a whole doctrine around these concepts developed by the US EPA, but it boils down to improving risk conclusions by using multiple bits of evidence instead of just one bit of evidence. So if you're trying to answer a tricky question, such as risk to biodiversity or ecological integrity, you might want to use multiple bits of evidence to support your risk conclusions as a way to make those conclusions a bit more robust and tackle some of the uncertainty that individual lines of evidence each have. That was a very high-level overview of the risk assessment framework. I do just want to highlight that it's not a silver bullet to the challenge of contaminant risk assessment for offshore oil and gas decommissioning. There's a lot of knowledge gaps that need to be overcome in order to effectively apply these this framework, particularly for more complicated scenarios, and some of those are listed there. None of these are new. A lot of this has been uncovered through the National Decommissioning Research Initiative's first phase of work, which kicked off in 2021. I've got some of our outputs at the bottom there. But if you do have any questions, I'd direct you to Rebecca von Helfeld, who was part of our project team when I was at Curtin. Now, it's not just the framework development that Tom and I have been focused on. We've also been trying to fill some of those knowledge gaps ourselves. So I'll quickly hand over to Tom to talk through some of the Mercury research at ANSTO.
Yeah, thanks, Darren. So I guess one of the things that we're finding when we've been looking at mercury, especially in gas pipelines, subsea gas pipelines, is trying to understand the speciation. Speciation dictates solubility, movement into the sediment or around the water, and then eventually bioavailability. So a lot of the time we're finding metacinnabar or that beta HGS as the main species, but also we need to be looking for dissolution into mercury chloride and then transformation into methyl mercury chloride. And Darren, if you could go to the next slide, please. One of the things that we're doing at ANSTO is using our reactor to make mercury radioisotope tracers so that we can follow very closely bioaccumulation of different species by differing organisms. And there's some examples of some data here where we're showing very clearly that methyl mercury is really easily assimilated from diet by a range of marine species. Mercury chloride as the inorganic but soluble form is assimilated through diet, but then also is eliminated fairly well, whereas metacinnabar, really insoluble, doesn't really get bioaccumulated through ingestion and ends up coming straight through the animal. And Darren, from the next slide, please, we're coupling this live animal radio tracing with then at the end of the exposures doing post-mortem imaging to show where the radioactivity and therefore where the mercury has gone in the animals. And again, this gives us some idea as to potential for transfer through the food webs as well as risk for human consumers. You can see there. So really happy to talk through that at some other point. Darren, I'm going to pass back to you now.
Ames is also interested in mercury research, and I'm glad Professor Beaumont introduced EcoPath with EcoSim and EcoTracer, because we've continued Rebecca von Helfeld's work from NDRI phase 1, but taken EcoPath with EcoSim and plugged it into a Python coding environment so we can start to integrate more high throughput, high performance computing applications. So we're looking to do tens of thousands to hundreds of thousands of model simulations with existing food webs to start to do those sensitivity analyses to help direct efforts in the lab or field to the most important parameters that we can update. Also do some model calibrations for EcoTracer, which is one of the challenges that we've had with the existing tool, and then start looking at spatial scales. So can we start downscaling some of these food web models to regions reflecting our oil and gas basins or pipelines or platforms? And we're hoping this coding environment helps us to do that. On the norm front, we're in the lab, so we've taken some radioactive scale material from a pipeline, amended it to sediments to look at toxicity, bioaccumulation, and mobility across a range of different organisms. For the mobility piece, we were as well interested in the reductive to solution question for that scale material. Is it going to start releasing radium and polonium into the sediment pore waters? And we used the technique called diffusive gradients and thin films with a specialized resin to do that. And just our last slide, we're interested in the fundamental toxicology as well. So Alex Vastic was supported by NDRI in undertaking a range of chronic ecotoxicology tests using gamma radiation with marine microalgae, and she's continuing her work in a PhD, also supported by NDRI, with us starting this year. That's the end of our presentation. Really excited for this panel, and thank you for the invitation to join you guys.